So I'd like to say good morning. Thank you for coming out. And as an alumni of the Penn State SAE student chapter and of GM, it's great to be here. We've got a lot of ground to cover, so I'd like to just dive right into the presentation. You'll notice a slight change in our presentation title. However, the flow of the presentation matches the flow of the original title, so we'll be covering eco-friendly, rapid prototyping, and mass customization topics, and related engineering trades among 4 of the 5 3D Systems print engines. But first, I'd like to share why SAE. So we like SAE because of the engineered applications that can scale. Here we have an example here. I kind of call this my double suck-up slide. Because it's a good example of 3D Systems work with an SAE chapter. We did some good work with Oregon State there. And my boss also went to Oregon State, so I thought I'd kill 2 birds with 1 stone. When I was at Penn State, we had the Ford hybrid electric vehicle. It was an Escort wagon. And I can tell you what, our wagon never did 0 to 60 in 3.4 seconds. So good testament to the Oregon State team here and being able to apply new technologies to get better, looks like intake manifolds there, for this Oregon State vehicle. So I mentioned why SAE, and so the next question is why 3D Systems. And just wanted to give you a 1-slide overview of our company so that you can understand the basis, the technology basis from where we're coming from. Our founder, Chuck Hall, invented 3D printing with the invention of the SLA machine back in the 80s. He's still active today in technologies, decisions, and road mapping. 3D Systems has over 1,300 patents in the space and a global footprint. And yet we make most of our machines here in the United States. The key point here is that we make not only polymer, but metals machines here. So if you get into 3D additive metals machines, we're the only major supplier producing machines out of the United States. We have customer-facing experience via our service bureaus called Quick Parts, where you can just send your STL file and we'll print your parts for you. And we have over 100 materials and do custom materials work. The focus of today's presentation is on 4 of the 5 3D Systems print engines and related engineering trades in the auto and aerospace markets. We'll be covering the 4 in bold on the left, so material extrusion, photopolymerization, powder bed jet fusion, and material jetting. And the first print engine that we're going to talk about is material extrusion. So when I came up with the title for this presentation, I went after every keyword that you could think of. And that's why we have the longest title that marketing shrunk down. But the first item that I targeted was eco-friendly, and we have a printer. We did a partnership with Coke, where we would take Coke bottles, plastic Coke bottles, and we have a special processing facility that will take those and make the filaments for the EcoCycle printer. And so the first trade, as we all know about environmental trades, I did some work with Oak Ridge on environmental trades for other engineering applications. Environmental tends to cost a little bit more. And so for us, the EcoCycle print engine, that's $1,300 retail versus $1,000 retail for a comparable cube. So it's a 30% increase there. But just wanted to plant the eco-friendly piece, and that we're looking to pursue that. Just think if you can scale this, there could be some good implications there. The other thing is, as we heard earlier this week from several presenters, if you could reduce the weight of a vehicle, and in this case we would propose with 3D printing designs, you could reduce the CO2 content. So I saw a lot of metals lightweighting earlier this week. I didn't see a whole lot of polymer lightweighting. But so if you're in the audience and you have some applications for polymer lightweighting or would like to talk more about that, I'd love to hear about it. We're also having cases where we see production level opportunities make sense. As a prior speaker mentioned, and as we're seeing, we're getting more and more into production. So when we talk about lightweighting, maybe you should consider 3D printing. So before we get into the production piece, let's first cover how most folks have come to know about 3D printing or additive manufacturing. used to work at GM, and I drive a Chevy Malibu, so I like the Chevy Malibu example here, using our SLS technology. So this is rapid prototyping, and the 3-minute video highlights SLA technology and SLS technology. Just thought it'd be of value because we are at an automotive conference, and just wanted to kind of show you our technology here. Had some good shots of our machines. There's an example of an SLA machine. So it's that. I'm using ASTM terminology here for the 7 different print engines. So I tried to genericize the presentation. So print engine number 2, vat photopolymerization. This is what Chuck Hull invented. You have the laser on the top, it shoots down into a vat, literally a vat of resin. And on a layer by layer basis, there's a little elevator that goes up incrementally. And you zap it with the laser, and actually you drop it down in this technology. Zap it with the laser, drop it down, and it drops down into the vat. And when you're all done, the elevator comes up and then that's apart. The benefits of SLA technology is that you have the best surface quality, some of the best surface finishes you'll find out there, and this machine is a real workhorse for the industry. You get really high resolution, so in the automotive industry we see people printing out dashboard size parts, but yet still attaining accuracies of 45 micron. So you can produce very large parts with high levels of accuracy. Talk about engineering trades. You can do castings with our technology. We have a resin and a build style that's called quick cast. And so what you do is you print the pattern, and then you do investment casting. And this is a great way to reduce your lead times on metal castings. You could go to, you see here for a 3-part test run, and there's a whole white paper on this that we can get you from 3 parts. We're able to cut our casting time down from 20 weeks down to 9 weeks, and your initial cost from 50K down to 90K. So, having worked at Rockwell, where we had large casings for our gear boxes that came from China, it may take 3 months to get a large gear casing like that. If I could do it in 3 weeks with a quick cast, I think that'd be a pretty powerful business case. So I think it's an exciting technology. I was taking with the theme of engineering trades. There's definitely breakpoints, and I want to be fair to our manufacturers here, and that we got a case study here we did all the way back in the 90s with Ford. But a lot of the breakpoint decisions still hold in many cases. So that's out there on the web as well. And the key point here is, and it was mentioned by the prior speaker, is that you got to pick your spots. But things are, that make or break line is starting to move from maybe 1,000 parts to 5,000 parts and so forth, depending on the application, materials, and what you target. So in this example here, we printed with the SLA machine 28 automotive door electronic levers, printed in 32 hours on one of our larger machines. It took 1 hour and 10 minutes each, and the material cost was $16.20. So, the moral to the story here is you just got to pick your spots. So here's an example where at the close of the last presentation, the question was, are you getting towards production? And the answer is yes. Our customers are driving us towards production level capabilities. We have a notional chart up there as far as, we're increasing our capabilities in 3D printing. That's in the industry. Quicker than injection molding is improving, and this makes sense when you've got a relatively newer technology compared to a more mature technology. We have a case study out on our website where a colleague of mine did LED light covers, and he printed them out on the SLA machine. And he was doing 30 seconds per part, and this approach of 3D printing polymers on this polymer-based SLA, it beat injection molding. So you got to, again, pick your spots, but we're starting to get more and more cases where on a production level basis it makes sense to do 3D printing for additive manufacturing. We we've seen examples where you can stitch parts together, but very often for newer folks into 3D printing or additive, I like to say, is it bigger than a bread box? Because our machines, you can see there, we got some people there, it's relative sizes. The smallest machine will be a 10 by 10 inch build volume, whereas the largest machine will be 60 inches by 30 by 22. And so that is like a little mini hot tub. And it's pretty impressive as far as the size of the parts that you can get out of there. We printed car engines out of that, the core, the engine block. So it's pretty exciting stuff. The next technology that we have is selective laser sintering. So if I keep with the ASTM academic terminology, that's powder bed fusion for polymers. And in this technology, what we do is we roll out some powder on a bed, we zap it with a laser, and then we put another layer down, and then we zap it with a laser again. This technology was vetted by Boeing. They use it for ducting on their planes, and very, very tough mechanical properties, and that's one of the benefits of SOS. Here you see the mechanical capabilities of SOS. Higher tensile strengths than competitive polymer 3D printed or additive technologies. SLS is great because you can use it as a functional prototype. So you can run tests on it. So here you see a child car seat, and you can see that we mapped out the strains and stresses and really put a lot of performance sensors on it and compared that versus injection molded plastic. And the curves all to basically match up. So see a lot of potential there for the SLS and functional testing. SLS is about 7 times faster than the material extrusion crane engine, so there's a lot of benefits there from the speed standpoint as well. And so here's where we get into some of the phrases that we like to use, such as complexity is free. What you have here is a case where you have 15 parts, and a number of different SKUs and custom tools, and that's the traditional method of manufacturing. But then if you 3D print it, you can do it with one piece. And so this is a classic, part reduction story. GE's done this a lot with their fuel injection nozzle. They've gone from 18 parts down to 1. So this is a classic engineering trade, and we use the words like complexity is free just to get people thinking. It's technically not free. You got to buy the machine, buy the materials. But we use that so that people can start to change their mindsets. With 3D printing, you really got to take advantage of the technology. If you just replicate what your existing part is without taking advantage of the capabilities of 3D printing, you kind of cut yourself short. So, in addition to complexity being free, airport is free. So think about this: if you're the Air Force and you have the Air Depot out in the Middle East, and you need some ducting parts, your plane went down, you can bring it right up if you got the design. Having worked for Rockwell, where we would have many different old tooling dies and many different old products that we'd have to keep on the shelves, it'd be great if you could just keep the file on the shelf and 3D print it instead of keeping all this volume and all this inventory. So with that, I'd like to move on to the fourth print engine that we're going to cover today. And this is material jetting. The neat aspect of this is you can have multiple engineered composite materials all in one build. So what we have here is like a toy car, and the center of that car is made out of rigid ABS plastic, but the wheels are rubber-like. So you could adjust the elastomeric properties of that build all in one build. And having worked when I was at GE, we did some wind stuff, and there's aero folks in SAE nowadays, right? So think about the aero application, you could have active control contours. So like you could have an airplane wing or a wind turbine wing where you have the wing, and because you have a flexible material in here, you can have pistons built into the wing to drive it and flex it. If you have elastomers built into the wing. So a lot of potential there, potential for simpler things such as integrated gaskets. I like this slide because I've participated in the top two items up there. We went after a couple of GE Open Innovation Challenges. And the first one, we have a gasketing for this application. We integrated the gasketing into the part. And the one on the right is we're currently down selected for the GE, NFL, NIST, and Under Armour Head Health Challenge. So we're going to help design a better football helmet, a better Army helmet to absorb shock better, and using materials such as this multi-material elastomer capabilities, combined with the lattice structures that we could do it only in 3D printing. So it's some pretty exciting stuff. We're looking forward to that. We got a lot of positive press with the same technology for Derby the dog. We're not sure if it's coincidence or not, but our stock went up like $3 the day Derby the dog went viral. Derby the dog is a dog that one of our employees has, and we 3D printed prosthetics for the dog, and the elastomeric part is on the nose and where it hits the ground, so it absorbs the shock. But then the central part is rigid. So that's Derby the dog. So that's a medical application for 3D printing, and there's tons of medical applications, and we get into that a lot with our metals business. Covered 4 print engines today for ASD Aram, and this would qualify as print engine number 3B, powder bed fusion. So again, similar to SLS, you lay down the metal powder and you zap it with a laser, and then go ahead and lay down another layer and zap it with a laser. So, this machine that you see here is coming out this fall. We've already announced it. It's 20-inch by 20-inch by 20-inch metal print. We do Thai aluminum, Reconel, cobalt chrome, all kinds of, metals are open systems, and we do all kinds of metal powders. We acquired a couple metal companies and over the past couple of years. So what we're doing is we're weaving in the best of breed for both those printer capabilities. So when to consider metal printing? I've been involved in a couple proposals for metals, and to me, the ones I've seen the most relate to heat transfer. Not to say that there's other applications. I think antennas is another one that I've seen. You want to look at, and we had a good example earlier in this session. So, conformal cooling is great. You could weave the cooling into the part itself, and you could get heat exchanger efficiencies that you couldn't get before due to the geometry just being 3D printed. You get great part accuracy and increased strength of mass ratio. Just want to give you a quick look of the resolutions that we get, 50 to 100 microns, and assuming the best surface finishes. We have a mechanical roller that adds an extra compression step, so when we lay down the powder, then we have a mechanical roller that compresses the powder, and this enables us to get the best surface finish. and that mechanical compression step also increases the porosity of our parts, so we have the best metal porosity. Got good build speeds, and as I mentioned already on the density piece, low porosity. And as far as the mechanical properties go, when you think of engineering trades, okay, I'm a golfer, and so that's how I relate to casting versus forged. And I like to think that I'm a good golfer, so I use forged clubs. But I really probably should be using basic intro clubs. But anyways, United Technologies CTO I saw in Wall Street Journal or somewhere was quoted as saying, okay, when you think about metal printing, think about metal printing as being stronger than cast, but not quite as strong as forged. And so I just think about that in terms of my golf clubs, and I'm pretty well set there. But we have all the information on material strength and capabilities. My colleague Cindy Brana is our metals expert, and you couldn't make it here today. So if you got metals questions today, please throw softball questions at me. See here. We had animation in this graphics. Oh, there we go. Okay, so there you see the conformal cooling, and as our prior speaker mentioned, it doesn't have to be an all or nothing proposition. You can combine additive or 3D printing along with traditional means of CNC manufacturing. And I think we're pretty close to the end. Oh, this is the last shot here of some metals additive, direct metal printing. The one I'm most familiar with is the tire molds in the center. So there's a major tire manufacturer that uses our machines for printing the molds that they use for bringing the tires out. So with that, I'd like to say, in summary, we've covered 4 of the 5 print engines that 3D Systems has. We've covered a number of different engineering trades amongst those. And if you have any questions, now's the time. Well, thank you.